Okay, so this is a short video on vector diagrams and like scale drawings for National 5 engineers. So you should by this point already have a little bit of coverage and a little bit of comfort in the concept of representing forces using basically lines with arrows on them. So we would call them vectors. So it indicates the direction of the force and it indicates the magnitude of the force. The magnitude is inferred by the length of the vector, but it's frequent to see magnitudes written next to them, or for them to have a name and then somewhere else the magnitude is stated. Okay. At National 5 we will resolve these vector diagrams using scaled drawings. That's why I'm working on squared paper. So this is a 5mm square. Every square is 5mm. It's typical that you would be presented with a partially complete vector diagram. The forces that the vectors represent would be considered to be acting on a point. Right, so these are concurrent systems. That is, all the forces are acting at the one point. So it would be common that you would have a vector identified. And a second vector identified. I'm just going to make this one straight up and down away to make life easy for the first example. And perhaps you are given the magnitude of one of these. And you are asked to identify what we call the resultant vector. So that's where we work out if these two forces were acting on this body, what will their result be? If you push this body up and at the same time you push it to the right, then the body will move up and to the right. So we could actually substitute in one single vector that replaces both of them, and we would call that vector the resultant. So in some instances you would have to be able to work out where that resultant goes. The process is always the same. You make up a parallelogram, a quadrilateral. So the idea is that the opposite sides are parallel. So I'm drawing a line the same length as F1 on the opposite side of the quadrilateral F1. And then I could do the same there if I wanted to. And where those two lines intersect, that gives me the point at which I can create the resultant vector, FR for resultant. So both of those two forces acting on that body has the same effect as this single force. This single force doesn't exist in real life, but what it does is it allows us to quantify the effect of those two input forces and measure the direction, and then it allows us to plan in a third force that will stop it from moving. So I'll get to that in a wee second. So we've got F1 and F2. I've realised I've just called both of them F1. F1 and F2 acting on a body that results in that movement there. We've got enough information to identify the size of that just by using lengths. The length of F1 is known. So what's that? 80mm. So what we want is a newtons per millimetre value. So how many newtons equals 1 millimetre? So all we do is divide newtons by millimetres. We're looking for a newton per millimetre value. So if I punch that into my calculator, 205 divided by 80 gives us magic number 2.5625. Now the idea is we are rarely asked for this number, but we'll very probably be asked to use it. So you don't always have to have it written down, you don't always have to have it resolved on a calculator. You could leave it like that if you wanted on your calculator, or store it in memory or whatever. Because if we now measure the length of any other force and multiply it by that number, that will tell us the magnitude of the force. So I can measure the length of my resultant, which I'm getting to be, what's that, 83? Yeah, 83 millimetres on that resultant. I can multiply it. I've already got the number on my calculator there. Multiplied by 83 gives us 212, 213. So my resultant is 213 newtons. In an exam setting, the marker will be given a range of values, something like they would work out what's an okay tolerance on that reading. If I'm getting it at 83, it's possible that people could get it at 81 or 85. So they'll do that calculation and then give the marker a spread of values there. As long as you're within that window, you'll get it correct. So what does this mean for the structural engineer? What it means is the structural engineer could consider that F1 and F2 would go to, notice we've done this without even working out the magnitude of F2, we don't need to because of the diagram serves its purpose. So the structural engineer now knows what the resultant force of those two is. The structural engineer now understands that this system is dynamic, this system is moving, there are forces acting on it and it's moving up and to the right. If the structural engineer then designs in another force of 83 newtons at the same angle but going the opposite way, so FR doesn't really exist. FR is the result of F1 and F2, but if we include this guy, F1, F2 and this guy, because this guy's opposite to the resultant and equal in magnitude, it means that F1, F2 and this new guy will result in the system no longer being dynamic but now being static. And we could describe the condition as being in static equilibrium. There are forces acting but they all cancel each other out and this body is no longer moving. That's why we call this vector the equilibrant. It is the force which brings equilibrium, brings balance to the system. So it's common that you might be asked to work out a resultant force or maybe an equilibrant. In order to work out the equilibrant, you've always got to work out the resultant first. That tells you the magnitude, and then obviously it's never been asked in an exam up to this point, but you would use a protractor to measure any angles required. So what am I getting there? 15, 16, 17 degrees. That's the process. The same process is exactly, the process holds true in that first example I've given you. The two forces are separated by 90 degrees, but it's possible that they could be separated by any angle other than 90 degrees. This process is the same. You make it into a quadrilateral, so like this guy here needs to be this parallel to the first one. You could then do another one parallel to F2 if you wanted, or alternatively just mark that same length on there. So what that length is 75, so I can go 75 along there. So that would be here, and that's my FR in there. Again, you'd have to know one of the forces. So don't get dismayed if you see a diagram where the vectors are at an angle to each other. It's exactly the same process. So what I'll do now is I'll stick a couple of questions up. You would have to work on some kind of grid paper to do this. I'll keep the lengths of F1 and F2, I'll keep them to multiples of 5 to make it easy to draw with a ruler, but you will have to be working on some kind of grid paper because you do need to make sure that you've got 90 degrees between the forces. Okay, so there's 4 questions, alright? You can see questions 1 and 2 have 90 degrees between the two input forces. Questions 3 and 4 have angles between them. You attack them all the same way. You're looking to create a diagonal line. You know what way the diagonal line goes by the way that the two input forces go. So F1 is left, F2 is down. So that means you want a left and down. Down and to the left. I've drawn this one a little bit funny. If you create a rectangle there and draw it down and to the right, that'll be wrong because F2 is up the way. So you'll need to watch out for that. How would you create that rectangle? Just draw F2 there, or F2 there and join it up. And that way you've got up and to the right. So the resultant force is going up that way in this one. Don't get confused, always watch out for that because they do that in exam questions where they mess about with the directions of the vectors. You have to be careful about that. Over here I've drawn F2 at 45 degrees. Remember, you'll have to inspect this squared paper, you have to count it on your screen or whatever. If you're doing these in class, hopefully you'll have a paper version of them, but if you're doing them at home then you'll have to count those squares to work out exactly how long F2 is. F2 is the hypotenuse of a right angled triangle, and that's what was it, 6 squares by 6 squares, so the angle is 45 degrees. When you're drawing this one, if you have to draw this one out, you're going to have to use a protractor. I had to use a protractor to draw it, you'll have to use a protractor to draw it too. Get the protractor on there and mark off your 30 degrees, and then draw that line 60 millimeters long in order to get the answer to that question. In all 4 cases, we're looking for the resultant and the equilibrant, the magnitude and angle. So don't position them on the page the way I've positioned them. They should all be positioned right in the middle of an A4 page. You know, the resultant for this guy is going to go away over here, which means the equilibrant is going to go away over there off the page. So be aware of that. Right, ball and shots.